This is part 5 in a series of videos in which I'm attempting to boot this Mimi 803 vintage computer from floppy disk. I've been sent some disk images and some copies of floppy disks that we believe are meant to boot this machine, but for some reason they don't seem to work. And what I'm doing is working my way through the machine and trying to figure out exactly why the machine still won't boot from these disks. Now, as you probably know, it's not quite as straightforward with floppy disks as just having the data on the disk. It needs to be in a certain format. The information in the disk headers needs to be correct. It needs to match the disk, and it also needs to match the drive that you're putting the disk into. And then the measurement circuitry should be able to lock on to the disk speed and start reading the raw data from the disk and turn that back into the stored data. It's not working on this machine, and the approach I've decided to take, partly to make some videos but also of course to try and sort out the problem with the machine, is to reverse engineer the code that is in the system ROM. It's a very simple system ROM on this machine. It really only consists of the bootloader to load data from the floppy drives into RAM and a very simple monitor program. What I've done so far is extract the data from the ROM and turn that into a disassembly listing. I went through in a previous video some very basic ways to use a logic analyzer to do some generic testing on a font like this. What I'm going to do in this video is do some more specific fault finding on this particular machine. Now, I did receive a comment on the last video that had skipped over the part of the boot up process and didn't really fully explain why the ROM is mapped to F000 when a Z80 reset vector is at 0000. I'm trying to avoid being too specific about the way this particular machine works other than for the floppy controller, but if you're interested, the general idea with most machines, and it does vary, every single machine's different, but normally, especially a machine like this that's intended to run CPM, and CPM needs RAM at the bottom of the address space, and that means that you can't just leave the ROM at 0000 because otherwise CPM won't run. So the way it normally works is there's something like a latch or a flip-flop. I believe in this case there's a PROM down here, so I think that may well be involved in some memory mapping. But normally the way it works is at reset there's a flip-flop or something similar, and it's used to map the ROM into apparent zero address space. Although we've got address up here of F000, as far as the Z80 is concerned, it's mapped down to address 0. And then you probably find that these first few instructions, these out instructions, almost certainly are intended to change the mapping within the system. And what it then does is it allows the Z80 to boot, see the ROM, and then it can configure the system accordingly. And from that point on, of course, all the addresses can be correct because the Z80 has now been vectored to the correct memory address. So that's basically how it works. I'm not going to go through that and how it functions on this particular machine in this case. It's not important for the fault finding we're doing here. The only thing to bear in mind is that if you are trying to trace through this with the scope, you might find that the addresses aren't, or the address lines aren't connected exactly as you might expect them to be. Also, this is probably a banked system as well, so there will be other complications involved as well. But for our fault finding task here, we don't need to get involved with that. All we need to be able to do is go through the code and be able to trace through and follow it through from address to address. So what I've been doing is going through this, figuring out the best way to approach this particular problem. We are most interested in the floppy drive controller chip, and we looked at the spec sheet for this, and there's a table with 4 addresses, and those 4 addresses are for the 4 registers that we need to be able to access within the device. And what we need to do is find out what address in the system they're mapped to. Many ways we could go about doing this, but what I'll do is I'll boot up the logic analyzer and show you the way that I've got this configured to detect what address those registers are mapped to. Okay, so what I have connected up on the logic analyzer is, again, we have the 16 address lines. They're connected to the address bus on the Z80. 8 data lines connected to the data lines on the Z80. The not read enable is connected to the read enable line on the floppy drive controller chip. The A1, A0 mini bus, that's just 2 bits, are connected to the 2 addressed selection lines on the floppy drive controller chip. So that's these 2 pins. That allows us to select the particular register within the device that we're interested in. Chip select is the chip select for the floppy drive controller. In-out request is the in-out request pin on the Z80, and then we have the other lines that at the moment we're not using. The only other line on here that we are using is the write enable, and again that's connected to the write enable line of the floppy drive controller. So if we look at the trigger, this is where we need to set up the analyzer to trap the address of the registers on the floppy drive controller. So the way I've gone about this is, it's the address we're looking for, so we can't enter that, but what we can enter are the A0 and A1 values. So when they're both 0, that's the status register within the floppy drive controller. Chip select will give us the chip select line for the floppy drive controller. In other words, when the floppy drive controller is selected, that line goes low. It's controlled through what I believe is an IO RQ, so in-out request from the Z80. So again, we can monitor that for an active low. And then finally, if we look at the write enable line, so this combination means that we should be able to trap a write to the status register on the floppy drive controller chip. Okay, so we'll go to the waveform display, arm the analyzer, and I'll press the B key on the MIMI to try and trigger a disk read. And as you see, we've captured some data on the analyzer. What we can now look at are the control lines. So if we look at IORQ, so in-out request has gone low, write enable has gone low on the floppy drive controller, and chip select on the floppy drive controller has also gone low. If we now look at the address that we've captured, bear in mind this is an in-out address, so we're looking really here at the bottom 8 bits of the address that's been captured, and in this case we can see that the address we've captured is 20 hex. So in other words, we know that the base address for the floppy drive controller registers is 20 hex. So this is the table for these registers. These A0, A1 lines are the 2 lines going into the device. So that's these 2 lines, and they're used to select the 4 registers. These are connected via a buffer to the A0 and A1 lines on the Z80, so we know that these registers will be addressed in consecutive memory space. We know now that the first one is at 20 hex, so we know we're looking for 20, 21, 22 and 23 hex for these registers. In particular, the one we're interested in most is the data register, because that's the one we're trying to read data from when the disk is being read. So any read from that address at 23 hex is obviously something we'd be interested in. So now we have this basic information. The next thing is, well, what do we do with it? So we now have the addresses of the 4 registers that are in the floppy drive controller chip, and we need to try and locate the part of the code that is responsible for initializing the controller chip and reading data from the disk. And one of the easiest ways of doing this is either to capture a particular event using the analyzer, or in this case, because the file is so small, it's only about 35 pages, so what you can do is just search through and look for the first instance of an in instruction. And the reason I want to look for an in instruction is, if we look at the spec sheet for this particular device, there are these flowcharts that indicate the initialization process, and they all start with a read from the status register. Now we know the status register on the floppy drive controller chip is at 20 hex and it's accessed through an in-out instruction. So what we can do is find the first instance in code of this and just set to trap on that address. And in this case the address that we're looking for is FO9F, and that's what we're looking for in this particular listing. So FO9F is here and we're looking for this particular instruction. This is the first read instruction from the status register. You can see I've been making notes as I've gone through this, and so we'll set this address and clear the rest of the trigger set points. And so we'll go into the trigger menu, and this is the address that we want to capture, so that's FO9F. And set all the other trigger parameters to don't care. It should still capture on some of these, but because there is skew in the way that the system works, it's easier to capture data if you minimize the number of lines that you actually have active in the trigger. And the last one, just clear that. And so what we're going to do now is capture on any hit on address FO9F. So we'll go back to waveform. I'm going to press the B key on the MIMI, and we can see that we have captured address 909F. And to see if we've got the right point in code, you can see that at that address we should be seeing a value on the data bus of dB. And so if we look at 909F, we can indeed see that we're getting dB, and the next byte should be 20. So if we scroll across, you can see that the next byte is indeed 20. So what I did from this point on is I went through the code using the analyzer to check what was actually going on in the code. And by looking at the instructions, so obviously what you're getting here is the instructions on the data bus, and you can see how it's jumping around and where it's going to, what addresses it's going to. And when you trace this all through and looking at the listing that we have, what you can do is start to create a more detailed listing. So if I find the relevant parts, I start to comment, I start breaking the code into chunks to identify what we're looking at. 909F is the start of the floppy drive controller initialization, so I've labeled it as such. And if we then start looking through what's in that block of code, what we can do is go through the instructions one by one, see what they're doing, and then I start commenting on what each particular instruction is doing. I can do this by referencing the data sheet, so I know that, for example, if it's looking for a certain bit value within the status register, I know what it's actually looking for in terms of the drive settings or parameters. And same with the instructions. If it's an out instruction, we know that we can look at the data sheet and see what particular value is being sent to the disk drive. We can confirm that what's being sent out is correct by looking at the analyzer, and we can also see what jumps are being carried out. So in this case, at this point, I had a call to an address. So in the original listing, it just gives an address here, and if we follow the address through, we get to this point in code. But what I've done is, rather than just using the address, which was FOF3, I've changed the text in the file. So instead of saying FOF3, it now uses the text send FDD command, and I did a find and replace for all instances of that in the file, and then I commented on what this particular subfunction is doing and traced it through to the return instruction. So I now know what this instruction block does. It's a small subfunction, and all it does is it sends a command to the floppy drive controller chip. loops around 10 times, and then it starts reading the status bit, and it's waiting for the busy signal to go away on the floppy drive controller, and then it returns. But we can now reference that by name. So back here we can see that where it's saying call, instead of it just being an address, it's now referencing the name of the subfunction. So I can go through and do that with all the instructions, and if you look through this process, it matches one of the flowcharts in the spec sheet for the floppy drive controller chip. And what it's doing here is it's loading the head on the disk drive. It's then driving to track 0. It's going to the correct start sector, and what it then does by the time it gets down to here is it's starting to look to read data from the disk. And so what I can do is use the analyzer to track through all this and just incrementally looking at various addresses. So for example, if we want to see if it gets to this address, we can change the trigger point. So if I now change the trigger to what is it, FOB7, and then we can re-trigger the MIMI, and we can see that we are indeed getting through to that point in the code, and we can continue to trace through, see if the values we're seeing are correct. So at FOB7 again we should be getting dB followed by 20, so we're getting dB and 20, and we just keep going through until we find something that's not working. Now the interesting part in this particular block of code, the bit we're most interested in, is that we know the data register in the floppy drive controller chip is at address 23 hex, and we also know that the purpose of the code is to read data from the floppy drive controller and put it into RAM. So this is actually a very small block of code. There's not a great deal in it, and the first part is initialization of the floppy drive itself. And then as we keep going through, there are various instructions issued. It's looking for index holes, etc. And we know this by looking at the value it's looking for on the flags it's trying to read. And this is quite a small function. It's only probably 40-50 lines. And by the time we get down to this part of the code, we can see this instruction. It's INI. If you're not familiar with the Z80, it's a very powerful instruction. It uses the C register as a port number, and it uses the HL register as a pointer. And what it will do is it will read the data in on the port number stored in the C register, and it will store it at memory location pointed to by HL. It will then increment HL. So it's a very powerful instruction, but it's obviously exactly what we need for reading data in from a floppy disk. So the question here is what's currently in the value in C, because the value we're looking for is 23 hex. If we go back up the code a little way, you may have noticed at the beginning of this code, if we follow it through and look at the various parts of the code that are setting various parameters, then what we'll notice is at this point in the code it's setting C to a value of 23 hex, which is the address of the data register in the floppy drive controller chip, which is the comment I put at the end of the line. Also, it's setting the HL register to a value of E000, which is where the RAM on this machine resides. So, in other words, HL is pointing at the start of the RAM, and the C register is pointing at the floppy drive data register. So when we then issue the INI instruction, we're going to read the data in from the floppy drive data register, and we're going to copy that data out to the address pointed to by HL. So the first byte would go to E000, and then HL will be incremented, and so the next time we read a byte, HL will point at the next byte, and that's where it will store the next byte of data. So what we're interested in here, of course, is trapping this address, and that is FOE3. So I'll change the analyzer to that address. So the address is FOE3, I'll arm the analyzer, press the B key on the MIMI, and although the MIMI is reading the disk, or trying to, you can see that we have not tracked this address. In other words, we never get to this point. Okay, now we know that we're not hitting the part of the code that we need to read the data in from the floppy drive controller. We need to try and figure out why. Now, I know that we're getting as far as this instruction, so just to confirm that, I'll set the trigger point here, which is FODB. And we'll re-trigger the computer, and you can see it reads that address perfectly. So we're seeing FODB, and the value there should be dB, and we can see it's dB followed by 20 again, and that is what we're seeing. So we know we're getting here, but we never make it through to the INI instruction. So something in this loop is failing. So the value of 1 that we've captured, if we look at the data sheet for the device, and this is the status register, and in this case what we're looking at really is a set of flags in the status register, and in this instance bit 0, which is the one that's set to give us a value of 01, means that the device is busy. So what happens next in the code is the code checks to see if the bit is set. So we're at this point in the code, and if it is set, then it's rotated into the carry flag. It's checked to see if it's set. If it's not set, it will jump through to this address, and if it is set, it will jump through, or just fall through to the next address. So we should be going through to FOE0. So if we go across on the data we've captured, we can indeed see that we're getting through to FOE0 because that bit is set. And what happens then is it looks at the, or effectively looks at the next bit, and does the same thing again in effect to see if there's any data captured. So if we look at the flags, again we can see that the next bit on the flags is data request. So this will be set if there's any data captured in the controller chip. This is what we actually want. We want this to be set. But we know it's not set because we only captured the value of 1, and because we captured the value of 1, then what's going to happen is we're actually going to check the value of that flag. It's not going to be set, and we're going to loop back to dB. So we should find that we're looping back to address dB, which indeed we are. And this will keep going round until the device is no longer busy, at which point it will exit this loop at this point, and it should take us through to an address of FOE7. So if I now set to capture FOE7, and we'll see if we ever get to that address. Re-trigger, and indeed we do get through to that address. So we know that this is stuck in a loop where the device is busy but it's never reading data, and that's kind of a strange thing because this is a bit of an odd construct anyway, but it is working right the way through this. We're going right through the initialization, we're going through the reading and writing of registers. Everything's working except that it's never actually reading any data. Everything else works, it's just there's never any data in the data register within the device. So I'll continue searching through this, but it does look like this is as far as we can go in the actual code because this is doing what it should be. So it looks like there is a fault, most likely in the data slicer chip. Unfortunately, I don't have a spare one to try, but it looks like that's where the fault lies. I'll try and get hold of a replacement to test. But what I'm really trying to show in this video is this is a very good and powerful fault finding technique. If I wasn't videoing this and talking, this would have taken probably 5 or 10 minutes. And you can see that we've gone right through, tested all the functions within the operation of the floppy drive controller chip. We know why it's failing, we know what particular flags within the device are being set or are not being set, and we know that no data is being sliced and put into the data register. So it gives us a lot of information. It also tells us exactly how the code works within this machine. I'll continue to document this so it's fully documented, but you can see it's very quick and easy to do this. You can pick out all these sub-functions, give them names, and it gives you a very powerful tool for fault finding, and it's very interesting to learn how these machines work as well. Okay, any comments welcome. Hopefully in the next video we'll have some progress on getting some data out of the floppy drive.